Welcome to the 15th lecture of the course Turbulence. So, let us start with brief recap of the topics we have covered in the last class. So, mainly in the last class we have started talking about vorticity, since vorticity is very important in the case of turbulent flow, because we learned at the beginning of this course that fluctuating vorticity is one of the important property of a turbulent flow, right. So, for any turbulent flow it should include highly fluctuating level of vorticity, right. So, the vorticity which is given as omega I tilde, as I wrote in the last class, epsilon I j k del u k tilde del x j, okay, where that epsilon I j k is our alternating tensor or permutation symbol. So, this is what is the vorticity, and we have also considered the other relation, that R I j rotation tensor, R I j rotation tensor is given by half epsilon I j k and omega k, right. So, this is what we have discussed in the last class. Then we have also derived the vorticity transport equation, and the equation, if we write it here, that what we got. So, let me write in initial notation, because this is the form finally we will use in this course. So, plus u j del x j equals to the stressing or tilting term, that is what our omega I j del u I tilde del x j plus this is your omega I tilde del x j del x j. Okay. So, this is the last term is the viscous term, and this term is the vortex stressing and tilting term, as we have discussed, and this is the total change of vorticity, which can also be written as this equals to your this particular term. Okay. So, del u I del x j plus nu into del 2 omega I tilde del x j del x j. Okay. So, this is what our vorticity equation, and it says the change of vorticity, which is in the left hand side, is due to the vortex stressing and tilting and the diffusion, viscous diffusion of vorticity, right. So, that is what we have learned in the last class, and then we have also talked about what that the vortex term in the equation of motion. So, the vortex term in the equation of motion, let me write it once again, which is also important. Okay. So, the vortex term in the equation of motion, and we found that equation as this equals to minus del del x I p by rho plus tilde, you use half u j tilde. So, plus epsilon I j k u j omega I tilde minus the viscous term can be written as nu epsilon I j k omega k tilde del x j, right. So, our momentum equation, the Navier-Stokes equation, can also be written in this particular fashion. That is what we have discussed in the last class, and so this particular term, if you see, so this is the static plus dynamic pressure. So, the inertia term, contribution of the inertia term in the dynamic pressure has been written in this particular fashion, and this particular term, as we said, is very important. Okay. This is the important term in the case of turbulent flow analysis, and this term is just like your Coriolis force if we would have written this equation of motion in a rotating frame of reference, right. So, in that case this particular term would have come as epsilon twice epsilon I j k u j tilde then omega k tilde. Okay. So, this particular term, so there is a mistake here. So, just let me correct it, I it is. So, it should be k. Okay. I am sorry. Okay. Okay. So, this if you would have written the this momentum equation for the rotating frame of reference, then this term would have come extra in the momentum equation, and this is due to that Coriolis force, and here 2 into omega is the that rotating frame of reference, I mean the angular speed of the rotating frame of reference. So, 2 into that angular velocity omega k or capital omega tilde we have used, please note that. So, if we do not use tilde, that means that is actually our mean vorticity, that is what we are going to consider from next onward from after some time. So, 2 into omega k tilde is nothing but your vorticity, okay. That is what we would like to mean here. Okay. So, if we would have written that momentum equation for rotating frame of reference which is rotating at this particular rate, then we have got this particular term in the equation, or equivalently we can say this particular term for this non-rotating frame. Suppose there is a vortex line and that particular vortex line will experience a leap force, and that amount of that force is this much. Okay. So, that is what the meaning of this particular term. Okay. And this is the viscous term which has been written in terms of vorticity. Now, one more important point is that suppose let us consider the E rotational flow. For E rotational flow our vorticity is 0. Okay. Flow is E rotational means vorticity is 0. So, in that particular case this term is 0, this term is 0. So, we end up this equals to this. So, in that case actually this is the dynamic pressure. So, this dynamic pressure is coming from the your inertia term. Okay. So, that we end up ultimately to the Bernoulli's equation, that is what it says. Okay. So, all right, we have discussed this equation in the till this point we have discussed in the last class. So, today we are going to consider this particular equation for a turbulent flow. If we would like to consider this equation for a turbulent flow with the decomposition of ui as ui tilde, just like our previous case ui, and our omega I tilde we can write as capital omega I, which is our mean vorticity, plus your omega I. So, this is the fluctuating vorticity, right. So, this is what with this consideration, with this Reynolds decomposition okay, of vorticity and velocity, we can write this equation as follows. Okay. So, what we can write. So, this particular equation then we can write u I plus small u I del t after using this Reynolds decomposition, then time averaging of this particular equation. So, that is what I am writing here. So, that means sorry. So, this particular term then we can write this del xi, okay, and here it is going to be p plus p plus small p by rho plus this is half, this is going to be u j plus small u j, u j plus small u j. Okay. So, time average of this term plus your epsilon I j k u j. So, u j plus small u j plus your omega I plus sorry it is k, omega k it is. Okay. So, this is omega k plus small omega k, okay, average of this, and this particular quantity we can instead of writing in this fashion, we can also, I mean, directly this is coming from this particular part, or sorry, from the viscous part of the velocity or momentum equation. So, let us keep this as it is for our further easier comparison which we are going to do in this particular analysis. So, this is going to be our then u I plus small u I, this is del x j bar. Okay. So, this is if we simplify this equation, then what we get, you see, if we simplify, this particular term is of course 0, because that u I and small u I, none of these small capital U I is not a function of time, and small u I bar is equal to 0. So, this left hand side is equal to 0, and the right hand side after time averaging, we can write this as I am just eliminating all the small algebra which is involved here, and directly writing that. So, capital P by rho plus this particular term will give us two term, one is this capital U j plus half small u j bar. These are the two dynamic pressure term will be there. So, one is due to mean flow or mean velocity, another is due to turbulent fluctuation. Okay. So, this is this particular term is the contribution of the turbulent fluctuation to the dynamic pressure. Okay. So, that is what it says, plus if we consider this particular term, then essentially we can write I j k, and this is u j k epsilon I j k small u j small omega k bar. Okay. This is what we get, plus the last term which is nothing but your this del 2 u I del x j. Okay. So, this is what we get after Reynolds decomposition and time average of this momentum equation itself, which was written in terms of vorticity vector, right. So, if we see that, as I said, this is the the dynamic contribution of the Reynolds contribution of the velocity fluctuation to the dynamic pressure. And if we write this particular equation, for example, for a two dimensional flow, let us consider this particular equation and write this equation for a two dimensional flow. So, let us consider first two dimensional flow with for which we can consider that u1 is there, u2 is there, and u3 is equal to 0. Okay. And once again that your u1 is much higher than u2. Okay. That is another condition, and del x3 is equal to 0, and we have only one vorticity component, that is your omega 3, which can be approximately be written as del E1 del x2. Okay. And another point here, this is much less than del x2. So, the streamwise gradient is very small as compared to cross stream gradient, that is what it says. So, this particular type of two dimensional flow, exist, for example, for boundary layer and wake flow. Okay. So, for wake and boundary layer, this kind of two dimensional flow can be seen. Now, if we consider this particular equation, let us now consider this equation to be 1. If we consider this equation 1, then that equation 1 can be written for this particular type of two dimensional flow, and in that particular case what we can get, we can write it here. Okay. So, see, for this particular case, so for two dimensional. So, this equation 1 for two flow as okay, then this particular equation can be written as 0 del x 1 capital P by rho plus half u j here we are considering the contribution to the dynamic pressure from the turbulent fluctuation is negligible for this kind of flow. Okay. With this consideration we can write this plus, okay, plus if you see that we are writing this equation for for I is equal to 1, for I is equal to 1 this equation then becomes, you see here, epsilon I 2 3 and epsilon I 3 2, I remains 1. So, in that particular case this two terms simplifies as u 2 omega 3 plus u 3 omega 2 plus u 2 omega 3 u 3 omega 2 bar, okay, and plus the last term. Okay. Last term your 1 del x 2 2. Okay. So, let us say this is your equation 2 and this equation is written for I is equal to 1. Please do keep it in mind. Okay. So, this equation we have written for I is equal to 1. If this is the case, then you see we can further, sorry, we will name this equation little later. Okay. So, or 0 is equal to, see we can write this as del p 1 by rho del x 1 minus this two term can be written as u 1 del u 1 del x 1, this is u 2 del u 2 del x 2. Okay. So, sorry, del x 1, okay, here that x 1. So, that u 2 summation is only j is equal to 1, j is equal to 2, j is equal to 3 is not absent in the equation. So, because u 3 is 0, that is why only j is equal to 1 and j is equal to 2 needs to be considered, plus this term. So, this term you see, what is this term? This term can be written as omega 3. Omega 3 is nothing but your del x 1 x 2, okay, and omega 2 is 0 or u 3 was also not there. So, this term is essentially 0 plus we are left with u 3 omega 2, and let us another step let us consider. Let us also consider the viscous term is sort of viscous term is sort of negligible. I think we have for x 1 we have written this equation. So, that means another term should be there. Okay. I am really sorry that I have made a mistake, and that is for x 1 that x 1 square should be there. Okay. So, so this is what we can consider, and considering or considering the viscous part of this equation is negligible, then you see this particular term is going to cancel out with this. Okay. So, we will be left with this term and this term plus these two term. Okay. So, that means our equation simplifies as u 1 simplifies as sorry it is yes. So, u 1 del u 1 del x 1 plus this term and this term will cancel out, we will be left with this term and that is u 2 del u 1 del x 2 equals to del p del x 1 plus these two term omega 3 u 3 omega 2 bar, neglecting the viscous term. Okay. That is what we have done here. So, let us consider this equation to be 2. Okay. Now, if you remember the Reynolds average Navier-Stokes equation, then let us write that in Reynolds average Navier-Stokes equation, which was this. So, Reynolds average Navier-Stokes equation, if you can remember, was this. Okay. Now, if we once again consider the viscous term to be negligible even in this particular case, because that particular equation whatever we have just now written, it is basically same equation we are writing, right, in terms of vorticity, that is what the difference. So, if we once again neglecting the viscous term, we can write this equation for this two dimensional flow, then we can write the same thing as for this I momentum equation x 1 plus u 2 del 1 x 2, and we are writing this equation same for I is equal to 1 only. Okay. Then if we are writing this equation for I is equal to 1, here we are going to get two terms. One is our minus 1 bar del x 1 plus del 1 u 2 bar del x 2. Okay. And the viscous term we have neglected. Okay. So, this is once again for I is equal to 1 only. Okay. We are writing this equation for I is equal to 1. Okay. And since we have said that we have considered a flow where the del streamoise gradient is much smaller as compared to your cross stream gradient, that means here this term considered to be approximately 0 as compared to the cross stream gradient. Then we can write this equation as u 1 x 1 x 2 del u 1 del x 2 is equal to minus 1 by rho del x 1. Okay. This particular term is your u 1 u 2 bar del x 2. Okay. Let us say this equation is our equation 3. Okay. Now, note this equation 3 and equation 2, they are for the same two dimensional flow. So, we can compare both these equations. One equation that both are actually momentum equation, one was written considering the vortex term in the equation and another was without the vortex term. Then we can compare this equation, and comparing this equation equation, comparing equation 2 and 3, what do we get? So, comparing equations 2 and 3, we get, what do we get? The gradient of Reynolds stress. See, this is what is interesting part. So, minus u1 u2 gradient or cross stream gradient of that is essentially equals to what? u2 omega 3 bar plus u3 omega 2 bar. Okay. And let us say this equation is our equation 4. Okay. So, if you see this equation, so in equation 4 you see what is the order of magnitude of this particular term. If we consider the turbulence scale is L as our previous considerations. So, then this order of this particular term is nothing but u square or ut square by L, right. So, order of this particular term will be ut square by L. Since the order of this particular term ut square by L, we can say order of this term also should be ut square by L and this term also should be ut square by L, right. Okay. If this is ut square by L, what I would like to mean, order of this term ut square by turbulent length scale L. Okay. If this variation in the cross stream direction scales with this L. So, then order of this term also ut square by L, order of this term is also ut square by L. But we will see just in some later considerations or class that omega 3 is actually ut by lambda, lambda is the Taylor microscale and this is ut. So, their value is going to be what? Ut square by lambda. So, that means in one side we are getting the order of magnitude of this is ut square by L, and if we consider omega to be ut by lambda, then we are getting the order of magnitude of that of this particular term is ut square by lambda, but that is ut square by lambda is much higher than ut square by L because lambda is smaller than L, right. So, if we would like to find out the correlation coefficient of this particular term or this particular term, this correlation coefficient goes as lambda by L. Okay. So, this correlation coefficient goes as lambda by L, which correlates or which scales with 1 by or which scales with REL to the power minus half, right. That is what we have seen in the previous class. That means, for very high Reynolds number, their correlation coefficient is very small. Since their correlation coefficient is very small, we can say they do not or this particular quantity and this particular quantity they do not correlate well. That means, why? One reason of this is their frequency is way apart. Okay. Their time scale, okay. The time scale of or turbulent eddies which is contributing to u and turbulent eddies which is contributing to omega are their frequency are not of the same band, they are way apart. That is why their correlation coefficient is not high, is much below than 1. Okay. That is what it says. Okay. Anyway, we will discuss this part little later. So, what it says basically, the turbulent eddies, the bigger eddies or the eddies which is contributes to this particular velocity is basically largest scale, whereas the turbulent eddies which is contributing to the fluctuating vorticity actually small scales. Okay. That is what it says. Anyway, we will come back to this little later maybe. So, what let us do now? So, now this is what we got it. Now, there are some analogy to be made here. So, let me do it here. So, you see this Reynolds stress u 1 u 2. If you consider that mixing length theory, then Reynolds stress, this can be written as u t L del u 1 del x 2. Okay. That is what we have learned. That means, the Reynolds stress. So, what is this? Is essentially x momentum transported in the u t transported by u 2 in the x 2 direction, in the this gradient direction. Okay. That can be written in this fashion. Okay. So, that means what we can do, del x 2, if we take the derivative of this in both the side, then we can write u 1 u 2 bar equals to what? Equals to, we can write del x 2 u t L del u 1 del x 2. Okay. So, here if u t is constant, okay, if the turbulent velocity scale is sort of does not vary with cross stream direction, then this particular thing can be written as u t L del 2 u 1 del x 2 plus u t del L del x 2 del u 1 del x 2. Okay. So, now you see 2D flow we have considered, that means your omega 3 is equal to what? Del x 1 del x 2 1 2. Sorry, this should be 1, this should be 2, I am other way around. Okay. So, we said that the flow we have considered, that is of this nature. Okay. That means, this is kind of negligible as compared to this. So, your omega 3 is nothing but your approximately this quantity. Okay. That means, this particular side we can write u t L, this is omega 3 x 2. Okay. And once again, this also can be written as u t, this is omega 3 del x 2, right. Now, you see, let us say this is our equation 5. So, you see the right hand side of equation 4, you see the Reynolds stress gradient, the Reynolds stress or cross stream gradient of Reynolds stress is having two part, okay, this plus this, and here also the Reynolds stress gradient is having two part, this plus this. Okay. Now, you see this particular term, if you see this particular term, so if we say that u 2 omega 3 is equal to this, why? See, when we wrote u 1 u 2 is equal to this, what we are saying? We are saying the transport of u 1 momentum, okay, transport of streamoise momentum by u 2 in the direction of this gradient del u 1 del x 2 can be written in this fashion. Then using this mixing length theory, analogously we can say that this particular term also is equivalent to u 2 omega 3. Why? Because this particular term then can be written as transported of omega 3 by u 2 in the direction of this gradient along that x2 direction. Okay. So, this if this particular term can be written as this, considering transport of u1 momentum in the x2 direction by u2 velocity, which can be written ultimately in this fashion, then this particular quantity can be said transport of omega 3 by u2 in the direction of x2, and which is equivalent to this, considering the equivalent vorticity, vorticity transport mixing length theory after Taylor. Okay. So, this is, that means this particular term then is equivalent to your u2 omega 3. But what about this term? What about this term? This term, you see, we cannot say, because this term then your u3 omega 2, that means transport of omega 2 by u3 in the direction of u3, that means in that case there should exist what? Capital omega 2, gradient of capital omega 2 in the direction of, in the direction of u3, but capital omega 2 is 0. So, we cannot say that u3 omega 2 is the transport of omega 2 by u3, we cannot say that. So, then what is this? So, this is related to the change of scale, that means this term anyway we can correlate with this. So, that means this is essentially, this term is this plus this is equals to your u2 omega, sorry, this is u3 omega 2. Okay. So, this particular term is related with this, and what is that? This term is going to be non-zero if the turbulent scale has a gradient in the direction of x2. That means, if we consider a flow for which the turbulence scale changes as you go away from y is equal to 0 towards y is equal to positive direction, then this term is non-zero. So, what is that? That means there is a change of scale in the x2 direction, and this change of scale, that means considered or taken care by this particular interaction term. So, this is essentially vortex stressing term. Okay. That means, due to the vortex stressing, the change, I mean the length scale is having a gradient in the x2 direction. Okay. So, that means this particular term is just like your the transport of vorticity by turbulent fluctuation, and this particular term is what? This particular term is essentially due to vortex stressing. Okay. So, that means the changes of Reynolds stress in this particular equation, the changes of Reynolds stress is due to changes of Reynolds stress in the cross stream direction is essentially due to two terms. One is due to the transport of fluctuating vorticity due to the fluctuating velocity u2, okay, and is due to the stressing of vorticity by the fluctuating velocity. Okay. So, these are the relation between the Reynolds stress. So, the changes of Reynolds stress with respect to x2 happens due to these particular two terms. One is due to the transport, another is due to the vortex stressing. So, there are two terms which contributes to change this Reynolds stress along y2 or x2 direction. Okay. So, that is what this significance of this particular vortex term in the equation of motion. Okay. So, that is what I just wanted to mention at that particular point of time, and as I said, once again let me say this. So, essentially our Reynolds stress gradient u1 u2 del x2 is equals to your u2 omega 3 plus u3 omega 2. Okay. So, I said the order of magnitude of this particular term is u2 square by L, provided del x2 scale with turbulence scale L. Okay. Then order of this term also should be ut square by L and order of this term ut square by L, right. But we will come to know a little later that omega actually of the order of ut by lambda and u of the order of ut. So, u into omega essentially of the order of ut square by lambda, which is, so here what is the mistake we are doing? We are considering the time scale or turbulent scale contributing to omega and contributing to this u are of the same scale or same frequency, which is not the same. Since it is not the same, okay, so this estimate can be considered as the maximum estimate, and using this we can normalize the actual estimate ut square by L to find out the correlation coefficient as our previous way of doing it. Okay. So, the correlation coefficient of this term, so correlation coefficient of that u omega, okay, can be found as ut square by L divided by ut square by lambda, which is lambda by L, okay. Or you can write this as time scale. To find the time scale or to find the time scale, you take this as this, okay. So, and this scales with what? In the other day, this scales with REL minus half, right. So, REL, this scales with REL minus half. That means, as Reynolds number is going to be very, very large, then this correlation coefficient is going to be correlation coefficient, which is this ratio, is going to be very, very negligible. So, that means their length, their time scale, which is this divided by this, okay, time scale, which is time scale contributing to vorticity, this vorticity fluctuation, and time scale contributing to this velocity fluctuation are then way apart. Since their time scale are way apart, their frequency is also way apart. That means their frequency is not same. That is why they are not well correlated. Okay. So, this says that the turbulence scales which contribute maximum to the u, that is largest scale, the turbulence scales which contribute maximum to the omega or vorticity fluctuation is small scale. Okay. That is why this correlation coefficient is not very high, it is of the order of lambda by L. Okay. All right. So, this analogy we will be using later on at the time of our order of magnitude analysis. Okay. All right. Now, this is what we have got it based on our the vortex motion in the equation of vortex term in the equation of motion. Now, let us consider the vorticity equation and its averages. Okay. Now, let us consider the vorticity equation which we found in the last class and I wrote today as well. So, the equation let me write once again to go ahead with the Reynolds decomposition and time average of that equation. Okay. So, once again let us consider the Reynolds decomposition, which is our u I equals to, can be written as u I tilde, considering u I plus small u I and omega I tilde, let us consider omega I plus small omega I. Okay. And if we substitute this decomposition into the above equation, so let us say this equation is our equation 6. Okay. Till 5 we could finish till now. So, if this is, then from equation 6, considering this from equation 6, we can write what? Del t plus u j small u j del x j j x j plus nu del 2 omega I small omega I del x j del x j. Okay. Taking the time average of this equation, we can write this. Okay. And if we simplify this equation, then of course, this part is going to be 0. Okay. I do not need to explain why it is so. I believe that you understand that, and then we are left with this plus u j del omega I del x j bar. Okay. And this equals to, from this we can write j del capital U I del x j plus omega j del U I del x j bar plus nu del 2 del x j del x j. Okay. So, after further simplification, we can write x j equals to minus u j del small omega I del x j bar plus j del u I del x j plus omega j plus nu okay. This is what it is we get. Now, another line of simplification can also be written. Let me write, after that let me discuss, equals to, see this particular term we can write as using continuity, this is u j omega I bar del x j, this we can write from the continuity, and this particular term we can write as capital S I j, and this particular term can be written as omega j small s I j bar, okay, plus nu del 2 omega I del x j del x j. Okay. Now, why this becomes this and this become this, let me explain you. Okay. So, y we are writing j del ui del x j equals to, we are writing this j s I j. Similarly, for fluctuating part as well. Why? So, that is what we are going to answer here. So, you see this particular part we can write as j, this particular part can be divided in two parts, that is what is your capital S I j plus your rotation tensor. Okay. So, let us say that rotation tensor is R I j. Okay. So, there are two parts we can write it. Okay. So, if you see this, then we will have this is equal to S I j plus R I j. Okay. And we have to show that this part is 0, right. Then only we can write this is equal to this. Okay. Now, why this is 0 is very interesting to note. Let us say your B I is equal to, say it is what? It is a vector, because j is a dummy index. So, that means it is a free index is I. So, it is a vector, let us say that vector is B I. So, what is that? Then this is j and this is R I j, and this is j R I j. R I j is what? Minus half epsilon I j k into omega k, that is what we have learnt. Okay. So, equals to half epsilon I j k j k, right. So, B I is equal to this. So, this is one equation I, let us say, and B I can also be written as, you see, minus epsilon. I just wanted to exchange the j and k, because both these are dummy indices. So, I can write k in place of j and j in place of k. Then I can write minus half epsilon I k j, and this is k j. Okay. Now, you see this is what? This is equal to minus epsilon plus, so one minus it will come here, j k, and this is k j. So, let us say this is your this. So, you see here twice B I from equation I and I 2, that this 1 and 2, twice B I is equal to this is same thing. So, this is 0, which says that B I is equal to 0. So, that means this is what our B I, which is 0, is equal to 0 from this analysis. So, this is equal to then this, or similarly we can write small or fluctuating quantities, this equals to your omega j small s I j bar. Okay. That is why we have written this quantity as this quantity as this. All right. Now, once again let us consider this equation for, once again let us consider this particular equation for this 2 dimensional mean flow we have considered. So, in that particular 2 dimensional mean flow, what we have what we consider? We consider that in that particular 2 dimensional mean flow only omega 3 will survive. That means, if we consider that omega 3 I is equal to 3, then we can write there will be 2 component of these. So, that means only I is equal to 3 is going to survive, and x3 is del x3 is 0. So, u1 and u2 is going to be there. So, in that particular case you are going to get u1 3 x1 u2 3 x2, okay. And this one what we are getting. So, this one is coming from here. So, here your I is equal to 3, right. So, del j j1 omega 3, this is what one component, del x 1 minus you are getting another component, that is your u 2 omega 2 del x 2, right, because considering j 1 and j 2, these are the two components which are going to be here. And what about here? So, this is it is going to be I is equal to 3 we have considered, right. So, that means I is equal to 3 we have considered, this is going to be your 3 and S 3 1 and 3 2. So, that means this sweat, this should be Z, okay. That is a mistake here. So, this is 3, this is 1 plus this is J 2 S, this is 3 2, right. Plus this is going to be your omega 3 S 3 J 3, okay. So, so essentially if we consider the major turbulent term in this equation. So, basically, so anyway this I think let us not disturb this term, let us keep it as it is, just 1 minute, I j plus nu x j, okay. And plus another term is going to be there, that is this term, which is nothing but this term. So, essentially from continuity equation, this also you can write as essentially from so you are going to have this equation. So, that is basically, let me write it, omega j and s, so s 3 j, okay. This is what is going to survive, and I is equal to 3, I am just going to change the I here, change the I is equal to 3. This is the equation we are writing, okay. So, this is what we will get it, okay. And if we see this, okay, so this term and here this two particular term. So, let me just this particular term also, it is bit involved, okay. So, please this is let me write as this, okay. So, this particular term let me write as u j, j let us keep it here, and this is 3, okay. So, this del x j, okay. So, this plus this plus this plus this for I is equal to 3, this is what we will get it, okay. So, let me once again this also let me change it. So, for I is equal to 3, we get essentially u j x j, okay. So, for I is equal to 3, this is the or this term, let me write it here itself. So, this term let me write it here itself. So, omega j s 3 j bar. Okay. So, you see this is what we get for the case of average vorticity equation. So, in the average vorticity equation for two dimensional mean flow, we have considered the two turbulence term are actually here, one term is here, another term is here. Okay. So, you see here that j is going to be 1 and 2 because del x 3 is 0. So, for that particular case if we consider this turbulent terms in this equation, mainly there are two gradients which are going to be there. One is del u 2 omega 3 del x 2, and here it is going to be 2, j is equal to 2 del u 3. So, this is this can be ultimately j you can take it inside. So, this term is equal to this, or using continuity this particular term you can write as del u I omega j del x j, and I is equal to 3, that is what we are writing the equation. Then this particular term or this particular term is essentially going to be del see this particular term can be written as this omega j u I considering continuity, okay, and the main gradient with respect to x 2. So, that is what, and this is going to be 3. So, this is what the term which is going to survive for this. So, in the next step we write for two dimensional mean flow case, then we can write the we are just concerned about the turbulent term. Okay. Let this term be there as it is. Okay. So, turbulent terms you will see what is going to be there here? It is going to be there that cross stream gradient u 2 omega 3 bar del x 2, and here we are going to get what? This particular term del omega 2 u 3 bar, okay, del x 2, okay, plus whatever it is there, we do not kind of disturb, let us keep as it is, okay, del x j del x j, because we are interested only these two terms at this point of time. That means, you see these two turbulence term can change the mean vorticity, okay. That is what it says. How they are changing? So, this particular term, what do you consider? This term and what we consider this particular term, this we consider this particular u 2 omega 3, you keep it in mind, u 2 omega 3 we describe this term as, what? Transport of omega 3 in the direction of u 2. So, that was kind of a force, and that was sort of a force or body force. So, this gradient is actually the gradient of this body force. Similarly, this was also our sort of body force, correct. So, this we explained, this is coming due to the vortex tracing term, right, keep it in mind. This is coming from the vortex tracing term, that is what we explained. So, that means this is also kind of a force which is going it is a force on a vortex line, but the vortex line is going to experience this force if it is there in a flow, okay, and this is a body force, okay, and this body force is essential, gradient of this body force then can change the mean vorticity, okay. So, what I am trying to say, these two terms we saw in the Reynolds average Navier-Stokes equation, when we wrote the equation in terms of vorticity, okay. In terms of vorticity, when we wrote the equation, these were the two terms we found there, and that was found to be that was also found to be gradient of Reynolds stress. These two term was found to be gradient of Reynolds stress, and these two term we also said in absence of rotation of the coordinate system, if there is a vortex line in the flow, that vortex line is going to experience a leap force, Rabin-Magnus effect, as I mentioned in the last class. So, that is the force this. So, this is essentially when there will be a vortex line in a flow, it is going to experience this force due to this vorticity, okay, in the flow. Okay. So, this is the force which is body force, and gradient of this body force then is changing the mean vorticity, that is what it says. Okay. So, the gradient of body force is changing the your mean vorticity. So, that is what is the explanation of these two terms. Okay. So, that we need to keep it in mind. All right. So, this is all about the your averaged vorticity equation and the considering the vortex term in the equation of motion we could explain till this point. Okay. So, anyway, I would like to stop it here today. In the next class we will talk about the entropy or the mean square vorticity and the dynamics of mean square vorticity. Okay. So, let us stop here today for this class. Okay. Thank you.